Yo, what's up? So day two.
Eventually, we'd get to the 400th number, whatever it is, that's what we would return. Clearly, in the worst case, this is going to be an O of k algorithm. I guess you could say O of n as well in the worst case. I mean, it depends on the k value. Now, the only possible way that we could optimize this is if we knew somehow from here, we knew among these choices, which one of them actually has the result? Which one actually has the 400th number? Well, how could you possibly know that? Well, potentially we could check for this guy, how many children does it have that are less than or equal to this? How many numbers start with a 1 that fall within the range? How many are there? And if that number is less than or equal to 400, including this one, I guess, then we should probably search this side. Now, if not, we just saved ourselves a lot of work. We can then ask the same question for this. Like, we don't have to go through that entire tree. We kind of eliminated that entire tree. And then we'd ask the same question here. Well, we just eliminated 4 or however many choices. Like if, let's say there were 300 choices here, we eliminate all of them. We can decrement that from k, and then we can say, okay, well, now we're looking for the 100th smallest number starting from this number. And then going to the children, we'd ask the same question. How many values are here? And suppose, let's say there's 200 values that are less than or equal to that range, which I don't think there are, but I'm just making this up. Well, then we would know, okay, well, the number is somewhere here. And so by doing it this way, we are going through the entire level in the worst case. So that's 10, that's a constant, not a big deal. But in this case, if that's what we're doing for every single level, like now 2 is going to have 10 children, and then we're going to ask the same question for here, like which one of these 10 children do we actually want to go down? So you can see that the time complexity of this solution is going to be determined by the number of levels in the tree. Like whatever level the kth value is on, that's the time complexity. So 10 times log base 10 of n. Now that's assuming that we can determine how many values there are along a path in constant time. But it's actually not possible to do that in constant time. But the algorithm I'm going to show you, like that's the whole complicated part of this, like figuring out how exactly to do that. And that algorithm runs roughly in log base 10 of n time. So just by seeing the time complexity, you can kind of imagine how we're going to do it. It's also going to be determined by going down levels. Then you could take this and multiply it by that. Now you kind of see how I'm getting the log squared. And I think there'd also be another constant in here, maybe 10, and then, that doesn't really make a big deal. So now let's figure out how exactly we can do that with a concrete example. We're going to start at 1. That's always going to be the lexicographically smallest number in the range from 1 to n. I could have a separate pointer which tells us what position we're at. Let's call it I equals 1. We're looking for position 400. I could do that, but when I actually code this up, I'm just going to decrement k.
Wait, so hahanapin hindi ko pa pala na I haven't put the code yet. Neetcode. Uh, so it's checking the second small. So based on my understanding, it's like from the last day, yesterday, yung same problem. Yep, like so lexicographical numbers and with the K is like the one in which you find the smallest. So parang range siya. So if it's K equals 3, you're gonna find the third smallest number. So that would be 11. But since it's 2, it should be 10. So it's gonna output the order in which not outputs an array, but it outputs the specific number of K. So let's continue.
Be another constant in here, maybe 10, and then, that doesn't really make a big deal. So now let's figure out how exactly we can do that with a concrete example. We're going to start at 1, that's always going to be the lexicographically smallest number in the range from 1 to n. I
Yeah.
could have a separate pointer which tells us what position we're at. Let's call it I equals 1. We're looking for position 400. I could do that, but when I actually code this up, I'm just going to decrement k because it's easier. It's more concise to do it that way. But I think for visualization, it might make more sense to say, okay, right now we're at the
Oh,
first
never
number. We
mind.
want to be at the 400th number. So basically, while I is
Implement.
less than k, we're going to continue our algorithm. Okay, so now we're
Is this
at this
equal
point. We
force?
want to know how many
No.
values belong to this entire thing, including this value. There's a couple ways you could actually think about this. One that I initially came up with was thinking of how to calculate just the children of this node. And while that works, the code ends up a bit more verbose than the other solution. So I'll kind of show you the more elegant one. It's to think of it in this way. We're here right now. So if we're at 1 and we need to get to 400, you could say that we need to take 399 steps. We need to take like that many steps in our DFS
Okay.
traversal. So that's one step, another step, etc., etc. Now, suppose that this entire tree has, including this one, 399 values. That would mean that starting from here, if we take 399
399.
steps, we're going to actually end up at this value. Why is that? Because this is one value, and then we have 398 children. So for us to jump to the last child, it would take 398 steps. On the 399th step, we'd be done with this entire tree, and then we would land on this guy. So thus, one elegant way to calculate this is to
Really?
say, well, if the total number of values in this entire tree, if I take that, add it to my current position, if that's less than or equal to k, then the solution is not within this subtree. Let me repeat that because
So to
this is
go
the
to
most important
another.
part.
So
If
the
it's
next sub
exactly
3.
equal, like we kind of showed that example, 1 plus 399, that would mean that this is the target. So I think that makes sense. Now, what if this was less? What if this was, instead of 399, it was 300? That tells us that there's only 300 in this entire tree. Thus, the 400th number can't possibly be in that tree, right? So that would mean that, well, we just eliminated 300 candidates, and now we're going to go here. We took 300 jumps, and now we're here. Now, if it was greater, suppose the total number of nodes in here was
400 what?
actually exactly 400 or maybe even 450, then it's obvious that the 400th value in lexicographical order is going to be in this subtree. And so in that case, we would go down a level, which would basically take this number and multiply it by 10. So we know that this guy has 10 different children, 10 all the way up until
To
19.
19.
So really, there's two choices. Either we go down, so here, or we move to the right over here. If we move down, we clearly eliminated everything over here in the tree. If we move to the right, we eliminated this tree. So now we understand that. Now, if you know that, you pretty much know most of the problem, but we just need to figure out that helper function. How exactly do we calculate the number of nodes in that particular subtree? Well, let's try to visualize it. We're going to do this level by level. So we know that this guy, I'm not going to draw all of them, so it's going to go from
So
10 to
first,
19. We know this
second,
is
third, fourth.
20. We want to count everything in this tree, so we can start kind of at the first level. It's always going to be a difference of 1 here. Like for this guy, we either want to keep going or we want to move to the right. The right neighbor is always just going to be a +1 from here. I think that makes sense. At the very least, this tree will have 1 value. So we take the difference between these two. 2 minus 1, we get a 1. Great. Now we want to know how many are in the next level. So we take this and multiply it by 10 so we get the smallest value in its level. Now from here, you might just think, well, okay, well, this level is going to have 10, and technically it will. And then we'll go to the next level, we'll go to 100, and this level is actually going to have 100 because consider this, like this will go all the way up until 109, but this one will have some children as well, 190 all the way up until 199. And everything in this range is basically all of the numbers that start with a 1 that have 3 digits, and there are 100 of them. And the next level will be 1,000. There's many ways to calculate this. The elegant way is like this. We could actually take the other value, like we originally started here and here, we could take this guy and also be multiplying it by 10. Because notice something here, this is going to be 20. And then down here, this is going to be 200. And so this
What?
way, we can just constantly take this value and compute the difference, which on this level will give us 10. Here it gave us 1. On this, it's going to give us 200 minus 100. That's 100. This is a pretty nice, elegant way, but the main reason we're actually doing it this way is because at some point, we might actually not want to include every single value on a particular level, and that's about to happen right now. So now we're going to get to the interesting part. We go here, it's going to be 1,000 and up until 1,009. Here, we're going to go to
Can't go 2000
1990
here.
up until 1999. But notice something. This is 2000. We're going to try to do 2000 minus 1000. So we're saying that there's 1,000 values on this level. I mean, technically that's possible, but our maximum value is 1361. So most of these are actually going to be invalid. In this particular case, rather than using 2000, we'd rather use 1361. So that's exactly what I'm going to do. So down here, I'm actually going to put 1361. Let's just do the calculation to see how it would work right now. On this level, how many can we include in this range? And remember that this value is inclusive. So right now we would do 1361 minus 1,000. That's going to give us 361. So what does that mean? That there's only 361 values in this range that are less than or equal to this number? What would that mean? That would mean, well, from 1,000 up until 1360, because, I mean, this counts. We're not starting from 1, we're starting from 0. So this is that range. But no, we're actually allowed to have 1361 as well. So basically what I'm getting at, that's like a long explanation for saying that we're not actually going to take this number, subtract it by that. We're actually going to take that number plus 1 and subtract it by that, because that value is inclusive. Okay, so we did it. And so now on this level, we're going to say there are 362. The plus 1 comes from the reason I just kind of talked about. So, okay, and now we're done, because now we're going to take this number, multiply it by 1,000, and we're going to get to 10,000, and we're going to see that, okay, this number, the prefix, is already greater than n. So at this point, we can stop. So how many did we count? In this subtree, there are 1 plus 10 plus 100 plus 362. Long story short, that is greater than k. So there are enough numbers here for us to have the 400th number. So we are going to go down this path. We're going to go to 10 now. And I'll quickly just go through a little bit of this. So if we were here, that was the first number in lexicographical order, and we're taking this and going here, multiplying it by 10, that's a jump of 1. So our I can say that we're now at the second position. But just because we're here doesn't mean that we're actually going to go down this path. Now here, we're going to make the same choice. Should we go down here, or should we go to its right neighbor, which would be 11? So let me kind of illustrate that a little bit. So right now, I is at position 2. Alternatively, you could decrement k. But now, same question. How many values does this subtree have? Well, we'll take 11 minus 10. That's going to give us 1. We'll multiply this by 10. We'll get 100, and then we'll get 110. Take the difference of these two. We will get 10. Same thing, 1,000, and this, which is that. How many numbers are like here in this side of the tree? Take these two numbers, take the difference between them. The reason we're still using this number is because this number is still less than or equal to that. If this number ever becomes greater than or equal to that, at that point we can probably break out of the loop. But the more important thing is that you use this number in that case. Well, this number plus 1. So here, this is 100 as you'd expect. And now down here, we're going to get to 10,000. And since that's bigger than n, we can kind of stop now. So we counted this many numbers that start with a 10. That would have been in this tree. And if you don't believe me, those numbers are 10 and then 100 through 109. And then like 100 of those values where we're going to go from like 1,000 up until 1,009. And then we do the same thing, I think, from 10 to 1019, et cetera, et cetera. So those would be like the 100 category. But long story short, this is 111. So if you take that and add it to our I position, we are going to be less than k. So we know that the solution is actually not down this path, and we are going to now try this path. And I don't believe the solution is going to be there either. Then we would try like 12, and we kind of keep going to the right until we found the one that had the correct like kth element, and then we'd start going down. Now, last question you might have is, well, what if we get to the last position? Well, first of all, if we did get to the last position, we'd pretty much know for sure that the child is down there because we can't really move further to the right. But those computations, I believe, will still work out because if we have 9 and we have 10, take the difference of those, it's going to be 1. Take 90, take 100, take the difference of those, that's going to be a 10. As you'd expect, we'll get to 900 and 1,000, take the difference, it'll be 100. So I do believe the math will be consistent in that case. While this might be like an understandable solution, it's definitely not easy to come up with. And to be honest, now that I'm kind of going through it, I can see why this is a hard problem. It's actually not that easy to understand. So let's code this up, and I actually changed my mind given the fact that I was explaining this in terms of having like an I pointer. I guess I'll just kind of use that just to be consistent. So we're starting at 1.
Okay, so we will try to solve now. I don't know if I should watch, but let's try to figure it out. Although it's a hard topic, so I guess we don't need to make an array, right? Since we're not gonna really produce an array.
1, that's like our smallest number, and the position of that element
Yeah, I equals 0.
is
Oh,
index
never
1.
mind.
We
It's
want to
one.
get our I pointer to be k, and at that point we'll return the current number. So let's just put that down here. So now
Return
we're going to
current.
say, while I, of course, is less than k, let's keep going. So what do we want to do? Either we want to move down,
So this is compare yung what neetcode said in it, which he compares. Oh yeah, it should be 1 because the ith the ith number will always be 1. It shows the curse 1, so its I should be also 1. So while 1 is less than k, which is what we're finding, 13, we're gonna do something inside that while loop. Yes, that's k. I think we go down if I'm right.
or we want to move to the right. So let's assume we have a helper function that I'm going to call count. And let's say, given the current position,
Okay, so this is a helper function. Oh, that's why it's not that it's gonna do abstracting function. OOP. Oh, no. Yeah.
it's going to give us the count of that entire
So
subtree,
count
including
the
the element
current.
itself, because that's going to tell us how
Oh shit. uh,
because that's going to tell us how many steps that we'll have to move to be to the right position. So if we wanted to move to current equals current plus 1, if we wanted to move to the right, this is how many steps we would have to take. Now, if
okay.
after taking that many steps, so
So we need to count the steps in which we count. So steps equals count per. This should be the answer.
plus steps, we're still less than k.
Okay, so if I, the index is when you add it to steps, so that means the steps is when you go down. So like, I'm not sure how the count works. I think it counts from, I don't even know if it's a tree or whatever this shit is. What? Yeah, I plus steps is less than
K, or we're
k.
exactly equal to k. That would mean that current plus 1 is the solution. In
Yeah,
either of those cases, we want to move to the right because either current
yeah,
doesn't have enough children. Well, yeah, that pretty much just means current just doesn't have enough children. The
yeah.
kth element is
Current
not going to be
plus
on that subtree, so
very
we move to the
close.
right. Otherwise, it does have enough, and therefore we want to move down. The way to move down is to take current and
Is
multiply
there
it
anything
by
else?
10.
Yeah,
Now, we also want to keep track of our
yeah. We're
current
gonna
position.
multiply it
If
by
we
10 so it
multiply by
goes
10,
down.
that's actually the easiest case. In our DFS case, that's just taking one step. So we can take our I pointer,
Okay, and then the idea here is wait.
easiest case. In our DFS case, that's just taking one
Oh, this
step.
is step
So we
for
can take
search
our I pointer,
algorithm? Oh, I don't really know what that algorithm means with school.
increment it by 1. If we move
So if we go down, we also increment the ith one. But how about this? Do we also implement it to one since it does go right?
move to the right, we have to take this many steps to do that. So that's exactly what we're going to do.
So
Increment
steps?
I by the number of steps. Now for actually computing the count, which
I
isn't
don't know what
super
the heck.
crazy, but I would say it's probably the hardest part of the problem. So let's do that. Give count and let's
It's fine.
say current and
We're gonna make
let's
the function
problem.
itself is
So
not
let's
main.
do that. Give isn't super crazy, but I would say it's probably the hardest part of the problem. So let's do that. Give count and let's say current and let's compute the number of steps. So I'm going to call that result and that's what we're going to return. And so we want its right neighbor, the current's neighbor. So I'm just going to call it that. Let's say neighbor and I'm going to say current right neighbor, the current's neighbor. So I'm just going to call it that. Let's say neighbor, and I'm going to say current plus 1. That's initially what's the case. And so remember, we want to keep going while our current is less than or equal.
Nay is assigned to current number plus 1. Okay. So para pag I think the idea here is if you go right, you need to also plus 1 it. So yeah, that's the idea.
Increment I by there. And then each time we
Wait.
computing compute the number of steps. So I'm going to call that result, and that's what we're going to return. And so we want its right neighbor, the current's neighbor. So I'm just going to call it
See.
that. Let's say neighbor, and I'm going to say current plus 1. That's initially what's the case. And so remember, we want to keep going while our current is less than or equal to the n value that's up there. So while that's the case, to the result, you could say we want to add to it the neighbor minus cur.
I'm still not very used to where you use while loop, so sorry about that. I'm not really good at but at least I think I have some rough idea in which it does something until it becomes false. So while reading this code, it means that in which if the current number is still is less than or equal to n, in which we append the neighbor minus current. So like yeah, oh, sure, to n, in which we s plus equals current minus name.
Cur. And then
A
each time we
minus
want to take cur and move down a level, so multiply it by 10 and do the same. And then each time we want to take cur and move down the neighbor minus cur. And then each
why?
you could say we
I think it was explained here, so I'm
want to
not sure.
add to it the neighbor minus cur. And then each time we want to take cur and move
We go
down a
down
level, so
again.
multiply it by 10 and do the same thing with the neighbor, multiply it by 10. The only catch is what if the neighbor is actually greater than n? Then
Yeah,
we'd be counting too many. So one way to do this is to say, well, neighbor could be equal to the minimum of itself and n, but not just n. We want to do n plus 1 for reasons I talked about. It makes the calculation work out. So
inclusive.
this will work. Obviously, you could take this and just substitute it here and do that, and then you can get rid of this line. So there you go. This is the entire solution, and it's definitely not easy. This is a hard problem for a reason. Let's run.
Yeah, you want me? So minimum of nay. Yeah, minimum of nay and yeah, and we inclusive it on minus curve. And then so we multiply it curve times equals 10. So to go down and cur right, cur again. Yeah, nay. You also go down to nay. I'm not sure what this code does. What happens if I remove it? Well, we can try. So the neighbor also goes down. It's confusing, but what if we get rid of this? You know what would happen? Run. What the fuck? Okay.
Run it. This calculation work out. So then n. Then we'd be counting too many. So one way to do this is to say, well, neighbor could be equal to the same thing with the neighbor. Multiply it by 10. The only catch is, what if the neighbor is actually greater than n? Then
Why
we'd
do you
be,
need to
and
multiply
each
this
time we
by
want to take
10?
cur and move down a level, so multiply it by 10 and do the same thing with the neighbor. Multiply it by 10.
Ah, wait, so you're comparing it. Oh my god, I'm being an idiot. So basically, this one, it's not really enough. You're gonna use this for this, so that you can count the steps. So like, in which you will com compare it was in which you will compare the uh in which if you count the current number, which is the steps, i-compare na yung like this thing, like this drawing, I think, if I'm right. Where's that drawing? This one, in which yung ima-minus, yeah, it's confusing, but yeah, it's fine.
What if the neighbor is
I'll figure
actually
that one.
greater than
Yeah, I
n? Then
shouldn't
we'd be
be even
counting
doing
too many. So one
hard
way to do
problems.
this
I
is
don't
to
even
say,
know
well,
what the
neighbor
heck
could
this
be
says.
equal to the minimum of talked about. Substitute it here and do that, and then you can get rid of this line. So there you
How
go.
long?
This is the entire solution, and it's definitely not easy. This is a hard problem
Yeah.
for a reason. Let's run it. And as you can see here, it works and it's pretty efficient. I think if I ran it again, it might do better. Well, anyways, thanks for watching. Check out neetcode.io for a lot more, and I'll see you soon.
Well, that's about it. So this is my second day. I know I'm not really coding. They think I'm copying, but it's fine. I'll I'll try to improve one step at a time. Five. Oh, what the?